to Chai and Y, and thank you for helping us beat our record of minimum monsoon attendance as well. We've doubled it actually, so it's quite good, and maybe some more people will file in. So it's a pleasure to continue the Chai and Y series with a session on chemistry by Aishwarika Mohanty. Aishwarika is she's from Odisha. She did her BSc in Bhubaneswar at Utkal College, went to IIT Hyderabad, did an MSc, and then came to TFR for her PhD. And she's been giving a lot of outreach talks as well at various fora that we have. And she works in the area of what is called ultra-fast spectroscopy. So can I really figure out what are molecules doing, what are the atoms within them doing, how are they moving around, etc. And she has some very nice stories about that to tell. So on that note, over to you.
Thank you, Arnav.
Okay. Now you start your screen share. Sure. Okay. And I'll monitor the YouTube. In case there are questions, I'll let you know. And you need to share screen. And feel free to ask questions. Okay, we can also do this hide floating. Close. You know, click some button. Oh, one second. Okay, now it should work. Yeah.
Sure.
Okay, all yours.
Okay. Okay, so good morning, everyone.
Okay,
thank you.
Remember, the mic is only for the online audience. For here, you have to speak out.
Yeah, sure. Thank you all for coming. So I'm Aishwarika. I am a PhD scholar working in the Department of Chemical Sciences. So
he's already given her synopsis and all that.
Yeah. Sure. So today I will discuss a bit about my research, and I will tell you what basically excites me as a PhD scholar. Okay. So the title of my today's talk is When Light Makes Twins. Okay. Now, when I'm talking about this light, the most important source of light that comes to our mind is the sunlight. Correct? Now, I presume that all of you know how important is this, not the sunlight, not just for us, but also for the plants who make their food and also create this oxygen that we breathe, right? Now, if I have just put a schematic just to show that this photosynthesis is very complicated. That consists of many complicated pathways, right? Now, inspired by this nature, we as a society have a different strategy to harvest the sunlight. Okay, using solar cells. So solar cells, if you know that it can harvest sunlight to generate electricity, right? So the most basic solar cell that I can talk about is the silicon solar cell. Okay. Now in silicon, I will try to simplify it for you all. In silicon, there are some space which is filled with electrons that we call it as valence band, and some are empty that we call it as conduction band. Okay. Now, as I put light energy, so I'm giving basically energy to the molecule or the silicon that we are talking about, the electron in the valence band can actually jump to the higher state, which is the conduction band. And as it jumps to the higher state, there will be a vacancy. And we call it as a hole, which is a positively charged particle. Now, if I have an electron and a hole, both of them are obviously oppositely charged particle, so they will attract each other and they will be bound to each other. Okay. Now, scientists have given it a very fancy term, which we call it as a exciton. Now, in my talk, I will use this exciton term very often. So just remember that whenever I'm talking about excitons, it means that there is a positively charged particle and a negatively charged particle bound together. Okay. Now, but then what do I do with it? So for that, what you can do is, if I have a exciton, then if I make a circuit out of it and separate the charges, separate the positive and negative charges, then I can basically create this current. And this is the basic principle of a solar cell, where you can harvest sunlight and create electricity, right? Now, but there is a fundamental challenge associated with this process. What? If you look at the solar spectrum, so the spectrum, basically what I'm showing over here is the x-axis is basically the color of the sunlight that is being, that falls on the Earth's surface. And y-axis is basically the intensity. Okay. Now, if you look at here in the spectrum, only 33% of the available, the sunlight that falls on the Earth, only 33% is available for us to use that in the solar cell. Okay, and other parts are lost due to different loss pathways, starting from this thermalization, which tells you that if I have a very high energy photon, which is basically a packet of light, if it is very high in energy, then some of the excess energy that it has will be lost as heat. Okay, so what you are doing is you are not putting every energy that you are getting from the sun into the solar cell. There are so many loss pathways associated with it. Not just that, during in the solar cell itself, there are also losses due to the extraction, right? So if I consider all these extraction losses, if I tell you all the list of, most of the, yeah.
I'm a bit confused.
Yeah.
You said there is some energy that the electron needs to jump. So where is that here, and what light is absorbed? And
so this has been reported for a silicon solar cell having a band gap of around 1.1 eV. For that, they have optimized this, right? So what I'm saying that in case of the thermalization, for example, I have a certain band gap for the silicon.
Okay, maybe later on, if necessary, we can explain this, the whole process.
Yeah.
Why a silicon cell cannot absorb all this.
Sure, I'll do that. So that's why, because of all these loss pathways, most of the solar cells that has been reported, the maximum efficiency is below 30%, right? So then if I have to enhance the efficiency for a better, making a better device, then what should I do? Then I have two options. Either I can inhibit the loss pathways that I just discussed. So people are rigorously working in this area, but this is not very trivial to, to inhibit all these loss pathways. But another interesting option would be that whatever light I have, can I generate more number of charges? That means with the same amount of light energy, can I generate more current? So that will, even if there is a loss pathway, but this the second option will enhance the efficiency of the solar cells. Okay. So for today's talk, I will basically focus on this option number 2, where I want to generate more number of charges or more current using the same amount of light that I have. Okay. So now, so the idea would be that initially the idea was that when one photon or the packet of light was falling on the silicon surface, I was generating one exciton, but then can I generate with the same amount of light 2 excitons? Okay, so that is the basic idea of this process. Now this is what we call it as a multiple exciton generation, and this process is known as singlet fission, which is the concept, the basic concept of my today's talk. Okay, so singlet fission means you all must be knowing about the fission, right? Breaking up something. So I will tell you in my talk how, not literally breaking, but how we can generate 2 products out of using 1 photon. And that's how we can generate multiple excitons. Okay, so this is the basic idea. I hope that's clear for everyone as of now. So now, before going into the complications of this singlet fission, let me tell you that these are some of the molecules which made up of this carbon, hydrogen, nitrogen, oxygen. So I have put a periodic table over here just to tell you that these are the elements that can be used to make these type of molecules which can show singlet fission. Okay. But now, for everybody's sake, let's first understand the basics as to what happens in a molecule. I have explained everything about a bit about the silicon, which is a semiconductor, but then what is there in the molecule? For that, here I have taken a molecule which is known as pentacene. So here there are 5 benzene rings connected to each other. Okay. Now here also, there are some space which is filled with electron and some are empty. In the silicon case also, I have showed you about the valence band and conduction band. Here, the molecules, although the concept is similar, but now you can consider these states as some stairs, for example. Now, as you go up, the energy of the stairs will increase. That means higher states will have higher energy and lower states will have lower energy. And electrons love to stay at the lower energy state because they want to be stable, right? And the rule is every state can consist of only maximum 2 electrons, right? Now, if I talk about the electrons, electrons are actually negatively charged particle, right? And it has some spin. So if a charged particle spins, then it will create a magnetic field. And if that happens, then I can consider electron as a tiny magnet, correct? Up now, if I have 2 magnets per se, for example, I have 2 magnets. If I have to bring 2 of them close to each other, then I can't put north pole towards north pole because they will repel each other. So I have to put north towards south and south towards north, right? And that's why here also the 2 electrons are, when they are close to each other, they will have to have the opposite spin to be stabilized. Okay? And in scientific terms, there are some terminologies I just wanted to mention that you don't have to go into the details. It's just that if I have both the spins opposite, then the total overall spin will be 0 because they will cancel each other. And we will call that as singlet. Okay? And if both of them are parallel, then we call it as a triplet because the spins will not cancel each other, they will add up. Okay? So you don't have to go into the details, just remember that if both the spins are opposite, that is a singlet. If both the spins are parallel, then that is a triplet. Now, then what happens if I put light onto a molecule, then in that what happens? So if I am putting a light, I'm giving energy into the molecule, right? So if I'm giving energy, then the electrons that are in the lower energy stair now can access the higher energy stairs. So it can jump to the upper stair, right? Now in the upper stair, either it can have a low, up spin or down spin, depending upon that. So as I told you, if I have both the spins opposite, then that will be a singlet. If both the spins are parallel, that will be a triplet, right? Now, it can form either a singlet or a triplet. But the interesting part is, if you look carefully, if one electron jumps from the lower stair to the higher stair, then there will be a hole left behind, as I told you earlier in the semiconductor case. That means in the molecules also, you can create these excitons, which are positive and negatively charged particles bound to each other. And now, if I can extract these charges, then I can use them in the solar cells. Okay. Now, let's come to the concept of singlet fission. Then what is the singlet fission that I'm talking about over here? And how I can generate two excitons per photon. Okay. So for example, I have these molecules in the ground state and I'm putting some light energy. So one photon, as I told you, can at a time excite only one molecule, not more than that. Okay. So if it excites a molecule, it will go to a singlet excited state. Why singlet? Because the spins are opposite, if you look carefully. Okay. Now, if there is a strong connection between the S1 state, which is a molecule that is already excited by a photon, then it can interact with another molecule which is still in the ground state. It is not being excited. If there is a strong interaction between them, then it would want to share its energy with the neighboring chromophore or the molecule. Okay? And if that happens, due to sharing of the energy, it will form a sort of a single entity that we call it as a TT pair intermediate. Okay? Now, if you look at here, the individual molecules, the spins are same, I mean parallel, right? So I can consider that as a triplet, right? But now, as I'm telling you that these two molecules are so strongly bound to each other that you now consider that as a single entity. So the overall spin will be 0 because individually they are triplet, but the overall spin will be 0, will cancel each other. Okay. Now with the here. Energy gets transferred from S1 to the other one. Yeah. So the spins that I'm showing over here, that can be different. There can be different permutation combinations as well. So I am showing just one over here, just for simplification. So now, as it formed, with time, all this, the strong interaction that it has initially, it will fade away, right? Because with time, every connection, strong connection will fade away. So that will form these two triplet excitons. That means in this process, what I did, I put one photon or one packet of light energy, but I am eventually generating two excitons. So now if I can extract the two excitons to use it in the solar cell, then what I'm gaining is, by putting the same amount of energy, light energy, I'm getting two charges. So in that way, I can enhance the efficiency of the solar cells, right? I think I hope I'm clear till now. Yeah. So okay. So yeah. So triplet concept. The singlet fission concept. Oh. Okay. Okay. I'll tell you. Just for the first question, just I wanted to answer that yes, if I directly am going from singlet to triplet, that is a spin forbidden process. I mean, it is a not very easy process. Okay, but if you look at this intermediate, TT pair intermediate, it is overall singlet. Okay, so there is an allowedness as I'm going from S1 S0 to TT pair intermediate. Now with time, it can just dissociate to form triplets. So I'm not going directly from S1 S0 to triplets. So that's the key point, that the TT pair intermediate that I'm talking about is basically the singlet state. That's why it is first allowed, and it dissociates with time to form two triplets. And about the triplets that I just talked about, I guess I was not clear, but I will go back again. Here. This one? Okay. So what I was saying is, for example, in this molecule, as I am considering these electrons as tiny magnets, so I have to be, if I have to keep both the electrons close to each other, then they have to have opposite spin. Otherwise, they will not be stable. But in the sense, but when I'm, for example, I'm exciting the molecule, the electron can jump from the lower energy state to the higher energy state, then in that state, either it can have an opposite spin, both the electrons, or they can have the similar spin. Okay. If they have opposite spin, if you look at here, so the electron spin is half, so the total spin will cancel each other, forming this 0. The S is equal to 0, which we call it as a singlet. Okay. But now, if both the spins are parallel, then we have to add the spin together to get S is equal to 1, and that is what we are calling it as a triplet. Yeah, we can have a doublet also. But here I'm not showing. So here, so doublet will have, it's like on the same molecule, if I have a two centers, then if I have a radical or something like that, and from there, you can get the doublets, not in the same molecule. So, yeah.
They have to be either parallel or anti-parallel.
Oh, yeah. It is only plus half or minus half. It has only two spins. It is plus half or it is minus half. So now, just to, I hope this singlet fission concept is clear, where you can basically generate two excitons per photon. Basically, you can enhance the charge generation. Yes. Yeah. That's a very good question, actually. So, yeah, so the question was that, is it only the pathway that the molecule can go? Is it the predominant pathway that molecule can go for forming these two triplets? Honestly, no. There can be different pathways as well. There can be competing pathways as well that can inhibit the singlet fission. But now, as a chemist, you have this control over the molecules, where you have to tune the molecules to make it go towards the singlet fission pathway. Correct. Absolutely, absolutely. So yes, absolutely. So what you can do is, so I will tell you in my further slides that you can actually study what are the competing pathways that is inhibiting the singlet fission, and you can tune the molecules accordingly to inhibit them, the competing pathways, to enhance their singlet fission efficiency. So yeah, so as I told you, this intermediate that I just talked about, it should dissociate with time to form two triplets. Then this intermediate is actually very crucial, right? So I will just tell you briefly about this intermediates. So as I already told you that individually they are triplets because the spins are parallel, but overall the spin is 0. So that is a singlet state, right? Now, if you look at, so it has been observed that these TT pair is called as a spin entangled species or an intermediate. What does that mean? For example, if I know that the total spin will be 0 and I have the spin idea of the spin of one part, then I can predict what will be the spin of the other. That is what we call it as a spin entangled intermediate. Okay. Now, just to give you all an analogy, initially the TT pair intermediate will be strongly coupled to each other. Okay, so just to give you all an analogy, here I have put the picture of twins. So initially they will be so strongly coupled to each other, right? But with time it will dissociate to form two uncoupled independent triplets. So the twins that I showed, the third twins, although they are twins, but they are so uncoupled that they are independent individuals, right? Similarly, although the two independent triplets that are formed after singlet fission, although that is coming from the same TT pair intermediate, but now they will act as an independent triplet states in excitons, right? Now, I told you about all these yeah. Yeah. So here I told you about the, this is the triplet exciton. You can have singlet excitons here. So the total spin, you're observing the total spin of the molecule. So you can have triplet exciton or singlet exciton. So that's why that is a triplet exciton. Yes, that is stable. Because if you, so what happens is, it is, if I have to come back to the ground state, for example, ground state is singlet. So if I have to come from triplet to singlet, that is a bit, that can be delayed, or that is forbidden. That is not that easy. That's why the triplet excitons that are formed have a higher lifetime. So that's how you have a advantage, that if you can extract them, because you have a higher lifetime, if you can extract them and put it in the solar cell, that can enhance the efficiency of the solar cells. That component which goes into creating heat. You are basically putting it into the excess heat into the forming two triplet excitons. Now, so let me just briefly tell you then what do I do as a PhD scholar at TIAFA. So if you look at here, I'm showing you a structure of a dimer. Okay, this is a bit complicated for you maybe, but this molecule is called naphthalene diamide or NDI. Okay, this is made up of this carbon, nitrogen, hydrogen, oxygen. So what I'm basically interested in, I have formed a, so we have a collaborator who have synthesized these dimers, where we have these two molecules and we have clipped them from both ends. Now why is that? For example, I have told you that you need to have two molecules close to each other in order to see the singlet fission. Okay, because you have to generate two triplet excitons, for example. Now, this is the minimal model that I can study. So the basic idea is, if I have a dimeric system, okay, so here as a chemist, what we can do is, we can, as sir asked, that we can tune the intermolecular interactions by changing the linkers that we are using. By that, what you can do is, you can enhance the efficiency at which the singlet fission yield will be the maximum. I mean, the triplets that you are getting will be the maximum. Okay, so that is the basic. So I'm interested in the fundamental aspects of the singlet fission, because that is the most crucial part before applying it for different practical applications. Because you need to know at the molecular level what is happening. how singlet fission is happening. Can we tune that? Can we enhance the efficiency in order to enhance the efficiency of the solar cell, right? So that is what in my PhD, I'm basically interested in the fundamental aspect. Now, but the most difficult part or the challenging part in this process is that this is ultra fast process. This occurs extremely fast. That means in femtosecond to picosecond, which is 10 to the power minus 15th of a second to 10 to the minus 12th of a second, okay, which is very fast. So tracking that in conventional spectroscopic methods, you cannot really see that in your eyes, right? That two triplet excitons are getting formed. So what you can do, that is then how do we capture this event? Okay. So before that, for that, our lab actually has been involved in, as Arnab told in the introduction, that we are interested in looking at the ultra-fast dynamics of different systems in the femtosecond resolution by using ultra-short laser pulses. Okay, so our lab has been majorly involved in this work. Now, let me tell you how that works. So, for example, this is a very interesting story that let's say you are watching a horse race, okay, and you want to take snapshots of the horse running, right? But your eyes do not have that resolution to tell you that is there any time point where all the four legs of the horse are in the air, because you can't see that. It is so fast, right? So this was the question that Edward Muybridge had in 1887. So what he did is he photographed a single horse and used a camera which has a very high shutter speed of around 0.002 seconds per frame, which is much higher at that time as compared to the conventional cameras that was available at that time. Okay. So now if you look at the snapshots in the upper row, the second and third picture, the four legs of the horse are in the air. But initially we could not resolve that because our eyes do not have that resolution, right? So, but he could do that by using this high speed camera, which has a shutter speed of 0.002 seconds. And this was actually foundation of this motion picture or this high-speed imaging that we have today. So then this was the idea. Then if I have to similarly watch the high-speed, ultra-fast dynamics of the molecules, then I need to have that fast camera, right? Ultra-fast camera with an ultra-fast shutter, for example, right? To watch what is happening in the molecules. Because as I tell you that singlet fission happens very fast in 10 to the minus 15th of a second to 10 to the minus 12 of a second. Then how do we capture that? For that, I need to have the high-speed camera. So that is the idea. And this was actually achieved by Professor Ahmed Zewail in 1999, where he got the Nobel Prize, where he could track the ultra-fast dynamics of molecules. Because I showed you the horse snapshots. So he could get the molecular dynamics in femtosecond time resolution. Okay. Now, how does it work? For example, let's say you are participating in a race. Okay. Now you will need a trigger or a starting point, right? A signal to start the race. Similarly, let's say I have a molecule which is in the ground state, and as I excite it using a light, so I'm basically triggering an excitation process or starting an excitation process, right? But in the light, when I'm putting the light, now the nature of the light should be an ultra-short laser pulse. So the time width of this pulse should be in the femtosecond. So what I'm doing is, when I'm putting this ultra-short laser pulse on the molecule, I'm triggering the excitation in femtosecond. So I'm starting the process in femtosecond. Now, as it is in the excited state in femtoseconds, now it will evolve with time. In femtosecond to picosecond to nanosecond with time, right? Now, as it evolves, I can bring some camera, right, to take snapshots of the molecule as it evolves with time. Now, the speciality of the camera should be that it should also a femtosecond pulse. But just to make things clear, here when I'm talking about the snapshots of the molecule, what I'm saying is, I'm not literally taking the picture of a molecule. What I'm doing is, you can think of it like the color of the molecule as an absorption spectra. So what I'm doing is I'm exciting the molecule in femtosecond time resolution. Okay. Now taking pictures or looking at the color, how it changes as it evolves in the excited state. And that's how we can track the excited state dynamics and what is happening in the excited state using this ultra short laser pulses. Because as I told you that singlet fission happens in ultra fast time scales, you need to have that much time resolution. Okay, I have not put it here. So we have this transient absorption spectroscopy. So we have a setup in our lab. So what we do is we generate these ultra short laser pulses. So we put, I will show you in my, I will tell you in my slide. So for example, now you might be asking that how can I generate this pulse then? So for just to make simplify the things. So for example, I have a rope and in one side it is fixed. In the other side, what I'm doing is I'm shaking it up and down. So you can generate this wave-like things, right? Now think if like another person is also doing the same, but with a slightly different frequency, for example. Then I can generate 2-3 such waves. And if I combine 2-3 such waves, they can form a bunch together with a very, very concentrated burst. Here I'm talking about the rope, but light waves also behave like this. Yeah. Sorry, can you be louder? Yeah. Yeah. So, so maybe I can, yeah, I will repeat the question. So the question is that if I'm bringing so many times the camera that I just showed you, that at different time points I'm putting so much energy into the system, then the system can degrade. Absolutely. So that's why what I just showed you is that all these snapshots are different experiments. So at a time, I'm taking a snapshot at, for example, 10 femtosecond. That is one experiment. Absolutely, yes. So I'm again bringing it at 100 femtosecond, picosecond, nanosecond. That's why. So our sample is good. So now, so that's why. So as I told you that light also behaves the same way. So that. Does it interfere with the energy of that molecule? I mean, correct. Oh, okay. So the question is, as I am capturing the event, does it interfere the dynamics of the molecules? So for capturing the event, the light that I'm using, it is of much lower energy. So it will not do anything to the molecule. So the higher energy is just the excitation, because I have to put it from ground state to the excited state. And then a lower energy pulse is coming just to take snapshot. It will not do anything to the molecule. So as I told you here, if I have 2-3 such light waves, okay, and I bring it together. So if I combine it together, it can form these short pulses with a femtosecond resolution. So basically, if you can change, change the length of this, for example, cavity that we call, because you have to, in the rope case that I showed you, that you have to fix the rope from both the ends, because in one end you are holding it, in the other one it is fixed, right? Similarly, in the light case also, you have to fix in between 2 mirrors, for example. And if you change the length between the 2 mirrors, you can basically change the pulse width. Okay, and this is how we generate the femtosecond pulses in our lab. So there is a setup where we generate it. Now, in singlet fission, then what we do, we take our sample in the container, which we call it as a cuvette. Then first, as ma'am asked, that first a higher energy, intense light will excite the molecule, which has been shown in the green pulse. Now, after that, I will bring the white light or another pulse, which will take snapshots of the molecule as it evolves with time. That means as it evolves from S1, S0 to TT pair to free triplet, I can observe what is happening, how can I, if I am tuning the molecule, I need to have an idea as to what is happening to the TT pair intermediate. How is it dissociating? Okay, because I have to enhance the dissociation to generate two triplet excitons. Correct? And using the ultra short laser pulses, I can actually see that, capture that event. Now, in this, this is a bit complicated, but just to simplify for you all, what we did is, as I showed you just this molecule previously, but in this paper, what we did, we changed the linkers, as I told you. So by changing the linker, what I'm doing, I'm changing the interaction between the two molecules, right? Now, as the two molecular interactions is very important for singlet fission, then I can basically tell you at what distance, what is the optimized condition at which we can get the maximum singlet fission yield. And this is very crucial for practical applications, because then you need to have an idea as to how we can tune the sample to get the maximum efficiency, right? Now, as I told you, this is the basic step. The most important part will be after formation of this TT pair intermediate, I need to dissociate it and then use it for practical applications. Now, you might be asking that, has it been applied anywhere or is just a theory? People have started using it. This is now a hot topic where one of the scientists in MIT, Mark Baldo, what they did is they used this silicon solar cell, okay, single junction silicon solar cell, and put a thin layer of this molecule which is known as tetrasin, another organic molecule. They put a thin layer of this tetrasin molecule, and this tetrasin molecule are actually known to show singlet fission. So what they observed is, when light is irradiated on the solar cell, in the silicon layer there will be formation of this electron hole pairs as usual. But with that, in the tetrasin layer, there will be formation of the electron and hole pair, but twice the amount. I'm putting one photon and I'm generating two excitons or two charges, for example. And the energetics of tetrasin and silicon is such that after formation of these charges in the tetrasin, it will inject its charges to the silicon layer. So here what they could observe is that charge generation efficiency was beyond 100%, it's around 138%. So if you have a one photon, one exciton process, you can never go beyond 100%. 100% is also very ideal, right? But using this singlet fission material, they could actually get the efficiency around 138%. Okay, and that's how the theoretical efficiency can increase from 29% to 35%, which is significant, because doing this also requires years of research. Okay, now, but as it is an evolving field, I will just tell you what are the existing challenges that we have. The first challenge will be that although we are generating this TT pair intermediate, in the singlet fission, then you need to dissociate that. If it is not getting dissociated, then there is no point of singlet fission there, because it will just recombine and lost as a heat or something like that. Okay, and the second challenge will be when we are injecting from the tetrasin layer to the silicon layer, we need to avoid the losses while injecting. So if we can, till now these are some of the existing challenges. If we can inhibit these challenges, then that will drastically enhance the solar cell efficiency. Okay, so now when singlet fission came into this, when people started studying the singlet fission, initially they started applying this in the solar cells, but now this has gone beyond the solar cell. Another interesting application I just wanted to mention is in photodynamic therapy. This is one of the cancer treatment process where what people have done is, in this process what happens, you have a non-toxic dye, okay, you put it into the patient's body and put light, okay, and upon light irradiation, it will form these triplet states upon excitation, and these triplet states can actually form this reactive oxygen species, some reactive species that can kill cancer cells. That's the basic idea of a photodynamic therapy. Okay, but now in singlet fission, there is an advantage because now you are generating 2 triplets per photon. So with putting the similar amount of energy, what you're doing is you are producing twice the amount of triplet states and hence twice the amount of reactive oxygen species. Okay, so the efficiency of this photodynamic therapy will be drastically enhanced using this singlet fission process. Okay, so with that, just to conclude, the concept is that this has been a very interesting topic which has gone from fundamental studies to its practical application in various fields, starting from solar cells to even cancer treatment. But it is still yet to be commercialized, but this has a high potential to have a huge impact on not just in solar cells, but also in different medical therapy. Now, before concluding, formally concluding, just to introduce our group. This is our group in TFR. I'm working with Professor Jyotishman Dasgupta. So, as I told you that we are interested in studying this ultra-fast dynamics by using ultra-short laser pulses. But other major part of our lab was also involved in doing this organic reactions in water. So in chemist, if you have some idea that organic reactions, doing it in water is not that easy because the substrates are not soluble in water, but we are using some cage, what we call as a molecular cage, and inside that we are doing organic reactions in water. Okay, so you all are welcome to visit us anytime. So with that, I just want to acknowledge few people. Arnav and Ullas and Chan White team for giving me this opportunity. My guide, Professor Jyotishman Dasgupta, for all his inputs, and this picture I have taken from him. This is the sunset at TFR and TFR Mumbai, of course, and all of you for coming and asking so many questions. Thank you so much. Yeah, I just showed you earlier that in photovoltaic cells, for example, the first challenge will be the triplets that you're generating is slightly lower in energy, right? So the amount of current, if you have to generate the amount of current, the voltage basically, it will be better if you have a higher singlet state, that because the singlet state will form these 2 triplets. So if your singlet state is higher, then the 2 triplets that are getting formed, the energy will also be higher. Another part is that the TT pair dissociation, because in solar cells, you are taking it as a film, correct? Now in film, dissociation can happen or recombination can also happen. So the TT pair that is getting formed, instead of dissociation, it can just recombine. So this recombination pathway we need to inhibit. And also we are using as a layer of singlet fission material in the photovoltaic devices. Okay, so injecting into the silicon layer is also a challenge, because during that process also the many loss pathways can happen. So engineering all of this will take a bit time to commercialize it, and that's the. Stop share. Stop. This happens only with a benzene kind of a molecule, or it is? There can be other. Okay, so the question was, does it only happen for the benzene-like molecules? Not really. There are other. It's like organic molecules made up of carbon, hydrogen, nitrogen, oxygen. There are different varieties. It's just that there are some factors that you need to, because correct. What is that? Because you have to generate 2 triplets from one singlet. So you have to have that much energy to divide it into 2 triplets. If the singlet and triplets are very close by, then that will not form that. And another thing is, as I told you, S1, S0 interaction will lead to TT pair intermediate, right? So the coupling between two neighboring groups should also matter. If the coupling is high, then they can immediately form this TT pair intermediate. If the coupling is not substantial, then there is a delay or there will no formation of TT pair. Tetracene. Yeah. So this is, so the pentacene, tetracene, these are one of the most established molecules that show singlet fission.
Established, optimized.
Yes.
Because when you said engineering,
Yeah. So
optimized.
Yeah. So there are two parts. There are people like me who are studying the fundamental parts, and there are people who are doing it for the practical application. Now, doing it in the practical application, in the fundamental study, I'm using a dimer. In the practical application, you have to make a film out of it. So there you have to again re-optimize to see. So in the fundamental study, we actually know that what is the distance should be there to optimize, to get the enhanced efficiency. But in the film also, there can be other factors. So in the practical application also, you need to optimize the conditions by which the singlet fission can enhance. Yeah.
So you're measuring these, the camera, you take pictures
Yeah.
times, and you said transient.
Absorption spectroscopy.
Just tell us exactly how.
Yeah. So maybe I can show. Okay, I can share again. Yeah. So yeah. So in transient absorption spectroscopy, what we do is, yeah. So in so basic idea of this transient absorption spectroscopy is that you first use this, for example, what I showed you in the as the green pulse. This is a high intense pulse, ultra short pulse having a femtosecond time width. You excite the molecule which has been kept in a container, and then you after the excitation it will be in the excited state, and it will start evolve with time from femtosecond to picosecond to nanosecond. During that time, at the same point where the laser pulse initially was falling, then you bring another white light pulse, which will take snapshots of the molecule in the excited state. Now, snapshots means, as I already told you, it's not like literally you are taking pictures, but what you are doing is you are observing the color of the molecule as an absorption spectra. As an absorption spectra, you're looking at how the molecules is getting changed as it evolves with time from femtosecond to picosecond to nanosecond. And here, as I'm telling you about the singlet fission process, I can basically observe the absorption spectra of the S1, S0, TT pair intermediate, free triplets. As it evolves, I can have a time scale, idea of the time scale as to in how many femtosecond or picosecond TT pair is getting formed, how it is dissociated. So that's the thing. So basically, after we have a detector which basically detects the snapshots of the molecules at different time points, and we can get a molecular picture, motion.
Send one femtosecond pulse, which excites the molecule. After some time, you send a white light pulse and look at what is absorbed.
Yeah. So when you are exciting the molecule, some molecule will still be in the ground state because there is a probability how much will go to the excited state. So when you are bringing the white light, you are observing both the ground state and the excited state. Then you have to subtract the ground state molecule to get only the absorption spectra or the idea about the excited state dynamics.
The white light is not very powerful, so it's not.
So it will just take the snapshots of what is happening in the excited state.
And the white light at 10 femtosecond, 100 femtosecond, 100 femtosecond.
Yeah, so if I tell you about the exact experimental condition, though, so the probe, the white light will always be there. We have a delay stage, we delay the pump as to excitation. So by changing the path length between the two beams, we can basically get a delay between the two pulses. And from there, you can get snapshots at different time points. You can, by changing the path length accordingly, you can get the how much time you want to take a snapshot.
These are all like there is one green light, and the next snapshot is taken when the second green light is. Correct? Because you can't do it on the same time.
Yes, these are different experiments.
But the green light will not do the same thing. Because every green light will have a unique pattern.
No, these are ultrashort pulses, so it will have a yeah. So
are all the combination. So in one case the TT could be 33%. Another case the TT could be 12%. That is completely right.
Yeah. So basically what we do is, between these two snapshots, we have that much time that it will go back to the ground state.
So that is fine.
Yeah.
But you're firing the gene again, right? What is the probability that it will replicate exactly the same number of TTs which were there in the
At the
10
oh no, that will not be there. As it evolves with time, obviously the states will also I mean, when you are bringing a snapshot at 10 femtosecond, what you are observing will be different from what you are observing at 100 femtosecond.
That's correct.
Yeah.
But in this case, because you can't be observing in the same time, correct? The same green light is getting shown 10 times, correct?
I think I understand your question. I think what he's saying is, how do you know that the response, the second time you fire the green, is the same as the response the first time you fired the green, or the third time or the fourth time? And the answer is that you have 10 to the 23
molecules. You're not putting
not the same one. Some other set of molecules will get excited, but that probability, if it is 32%, is always 32%.
Okay, that's what I want.
Yeah.
So these are just because you have enough molecules there. It might be a different set of molecules which are actually getting excited in the next pulse, but the average results are the same.
Yeah. So this is a bulk measurement that is in the solution. So we are getting an average picture. You are not literally doing it molecule by molecule. Yeah. Absolutely.
It should be of that lifetime only, then after that.
No, before it decays down, if you can extract that. For example, you have a reactive species. It has a certain lifetime. Before it decays, if you bring another molecule which it can react, correct. So before it decays down, you have to have another layer where it can inject its electron or charges. Sorry? Yes, that is a silicon layer where you have to inject. Yeah.
Will the application of magnetic field affect the lifetime?
Yes. So if you look at here, the TT pair intermediate, it has a magnetic field dependence to it. So based on that, you can alter the dynamics at the TT level. Yes.
Right now,
yeah, I have not shown it here, but people are actually studying about the magnetic field dependent of the singlet fission process.
can be like tuned.
It can be tuned. So sometimes it can also do the other thing. Charge separation is achievable. This is that is the experimental condition. Charge separation efficiency. Because what you can do is you can basically calculate how many charges you are generating per photon. So if you have a 1-to-1 correlation, they have experimental. Yes.
You are helping overcome the limit of silicon solar cell.
Absolutely, yes.
And right now, about 20%.
Yes, from 29 to 35%, but it can go beyond if we can inhibit the loss pathways as well.
how better it can get?
It should come beyond like 40, 44, but beyond that you have to think. Sorry?
29 theoretical limit is 44. But
Yeah,
this kind
44.
of thing can actually go 130 or
That is different. Okay, let me again.
Internal efficiency versus what?
I'll again tell you. There are two numbers. Now, this is the charge generation efficiency. That is 138%. This is the efficiency of the solar cell. These two are different numbers. The 138% that I showed is like you are putting one photon, you are generating one charge. Then if you are doing that, the maximum you can get is 100%. But by singlet fission, you are going beyond 100% to up to 138%. 29 to 35%. Correct. Yeah.
there you say that upper limit would be 44.
Yeah.
There is a 22% jump.
Sorry?
The number that shows were around 33%, not 29%.
No. This that was the I'll tell you. Yeah, that is the available.
There's a maximum that is 39%.
The silicon one, but other things have have higher efficiency, but that has also other limitations. Every system has their limitation, pros and cons. Correct.
Okay, maybe we should have a tea break and we can come back and discuss it.
Just to tell you here that 33% is the available solar sunlight that we can use for photovoltaic devices. Here also, if you look at the efficiency, most of the solar cells that I showed you is 29%. And as I am talking about the silicon single junction solar cell, there by using this singlet fission material, the jump is from 29 to 35%.
The extraction losses that
Because you have to extract the charges. No, yes, during the glass or FTO, during that.
Maybe I'll come back.
maybe you would just like to mention what is the efficiency of photosynthesis in nature. I mean, of course, you are not talked about it.
Yeah, that
Let's say like when plants are using it.
that I can't tell you right now a quantitative idea. Yeah, one can do that, but obviously no, because there also the concept is one-to-one. So you can never go beyond.
Yes, sir.
Of course.
So science is in a way progressing.
Absolutely, yes. Yeah.
Photosynthesis is woefully inefficient. Its maximum efficiency is 2%.
But that
Typical
means
efficiency is less than 1%. However, leaves grow, leaves fall down, new leaves grow again. I mean, photosynthesis
It's not really static.
The volume is too much. Right. But if you look at how much energy is absorbed by the leaf versus how much glucose or carbohydrate or whatever you are making, the efficiency is barely 1%. But that is what feeds us. That is what keeps everything else alive. That's what we have to breathe. But it's not. I mean, it has other advantages. It regenerates itself. This is the biggest thing. Anyway, I think it's time for tea.
Yeah.
So,
Thank you.
Okay, the next topic. Where? Yeah. Okay. Stop the slide. Right. Can you just stop your slide share? So let me, before we wind up, let me just announce the next session, which is 15 days from now at Ruparel College. It's going to be on nanoelectronics. Joydeep Sakar, who's a postdoc, right, at TIFR. They have got some very cool results in the nanoelectronics group as well, which we will learn about. And after that, we'll see. We'll announce the next one in a bit. All right. Yeah. With this, we stop the live stream. questions are most welcome. Please have a cup of chai and come back. There are lots of very interesting things on why solar cells have a certain efficiency and why it is around 30% and why it doesn't go beyond 42% or whatever she said. Why you can't get higher, etc., etc. It's actually pretty simple. Okay, yeah.
We'll stop there.